So today we are talking about what we call improper integrals. Improper integrals are integrals with some sort of infinite limit of integration. So if we are trying to integrate from some constant a to infinity, or from negative infinity to some other constant, or if we're trying to integrate from negative infinity to infinity. Okay. All of these are improper integrals. And you might think that if we're looking at a function that approaches some sort of asymptote, let's say of y equals 0, as we're going towards infinity, well, you might think that that volume there from, I don't know, 0 to infinity, let's say, I color this in here, this volume here from 0 to infinity, not volume, that area from 0 to infinity, I don't know why I'm saying volume. You might think that area has to be infinite, but in reality, those areas can approach some finite value. It's kind of like when you take a half and then add a fourth, and then add an eighth, and add a 16th, and add a 32nd, and add a 64th. Well, that's going on forever, but it's not going towards infinity, right? It's approaching a finite value of 1. And that's what we're going to be looking at here with some of these integrals, is this area underneath the curve may or may not be infinite. It might be a finite value, it might come out to be 7, it might come out to be pi, who knows? Or it might come out to be infinite. And so the way we'll deal with this, because when we do integrals, technically the limits of integration have to be real numbers. Instead of integrating from a to infinity, we will rewrite it as a limit as b approaches infinity of an integral from a to b. So this a value will be like 1. We'll go from 1 to b, integrate from 1 to b, get an expression in terms of b and other numbers, and then evaluate a limit as b goes towards infinity. Same with the negative infinity, or with the negative infinity to infinity, where we break it up somewhere in between negative infinity and infinity at some value that's easy to deal with, and then evaluate from there. Does that make sense? How we're going to deal with these? Or no?
Yes.
Cool. All right. So I want this page here first. Sort of, I guess. Actually, let's just start here. Let's do this one. Let's do the integral from 1 to infinity of 1 over x to the 4th. So thoughts on this? Clearly, we have an improper integral because we're going towards infinity. So we're going to rewrite this as a limit, as, and pick a variable, pick any variable you want. We will use a, b, c, q, z. B. Nick says b. All right, the limit as b approaches infinity of the integral from 1 to b. Then I'm going to rewrite this as x to the negative 4th dx. And so all we have to do is integrate x to the negative 4th. What's the integral of x to the negative 4th? Negative 1 over 3x cubed, right? Up to x to the negative 3 divided by negative 3, and the x to the negative 3 drops to the denominator from 1 to b. And so then we'll just plug in b and plug in 1 using the second part of the fundamental theorem of calculus, keeping our limit there for now. Limit is b approaches infinity of negative 1 over 3b cubed minus negative 1 over 3. The 1 cubed being 1, right? Everybody good with that? All right. And as b goes towards infinity, what happens to negative 1 over 3b cubed? What does it approach?
0.
Approaches 0. And so what do we end up with? As b goes towards infinity, negative 1/3 is just 1/3. And so the value of this integral, the integral from 1 to infinity of 1 over x to the 4th is 1/3 of a unit. And we should know, I mean, a basic idea of what 1 over x to the 4th looks like, I hope, right? 1 over x to the 4th just looks like this. We go from 1 to infinity. We know that's approaching this asymptote of y equals 0. And the amount of area underneath this curve is finite. It is not increasing without bound. It increases and hits this value of 1/3 when we get to an infinite number of x values that we've attained. Good or no?
Can you just say that again? Like it hits 1/3, or it's going, the area under the curve is going to 1/3?
Yeah, it's approaching 1/3. We say that the area from 1 to infinity is 1/3. And this is an issue that we have with calculus. In calculus, we often treat infinity like it's a number, even though infinity is not a number. It's just, you know, I'm sure you all know, infinity is just the idea that numbers go on forever. But what we do is we do a little bit of a disservice to higher branches of math by saying that, or by treating infinity like it's a number in calculus. But it allows us to come up with these, you know, these values that we're getting very, very close to. It's the bound on what that area could be. It will never get higher than 1/3. Technically, it won't get to 1/3, but we say that it is 1/3.
Okay.
Yeah. Does that help answer your question?
Yeah.
Because we never get to infinity. If we got to infinity, the area would be 1/3. But we never get to infinity, so we never really get to 1/3, but it's 1/3 for our purposes. It is cool, isn't it? This is the part, so when we start to get into improper integrals and we start talking about series and these things that go on infinitely, we really get into some of the really cool aspects of higher math that you can, you know, there's a lot of really cool things you can investigate and see using these, basically, I just want to say using infinity. There are a lot of really cool things you can think about and see. And some of these we will, you know, I'll talk briefly about them. They're not all exactly related to our class, but some of them are really cool. I think maybe it will be inspiring to some of you to hear about them and make you want to study math, because they're really quite interesting. We'll talk about, maybe if we have time today, we'll talk about one at the end. So it's a fun one. All right, so the limit that we got there was a finite value, right? On that first one, we got a value of 1/3. So what we say is that this improper integral converges to a value of 1/3. If the limit that we get doesn't exist, we then say that the improper integral diverges, and that there happens to be then an infinite area underneath that curve as we go towards infinity, or towards negative infinity, or to both sides, for example, for the one we're looking at here, e to the x. And, so in the third thing that we were talking about here down here, this one, when we go from negative infinity to infinity, both parts of it have to be finite for us to say that this integral converges. But if one or the other, or both parts, don't exist, if the limit doesn't exist, then we'd say that it diverges. So if we looked at something like negative infinity to infinity of e to the x, now I would hope right off the bat, just knowing what e to the x looks like, you should be able to tell me if this converges or diverges. Could you do that? What does e to the x look like? well, you know what it looks like. I'm going to put it up here anyway. So e to the x, right? It's got a horizontal asymptote of y equals 0 as it goes towards negative infinity to the left. But as you go towards infinity, it's increasing without bound. I mean, there should not be a finite bound on this area. I mean, especially over here to the right, where, I mean, this is just getting massively large as we get to large values of x. True? You guys agree with that? I hope. Yes. Oh, good. Okay. So we should be able to say that we know that this integral diverges. But just for fun, let's split it at 0, because 0 seems like a good place to split this one. And look at both sides of it, because it'd be interesting to see, perhaps on the left-hand side, if it approaches a finite value if we just went from negative infinity to 0, let's say. So let's turn this into the integral from negative infinity to 0 of e to the x dx plus the integral from 0 to infinity of e to the x dx. And in doing that, we need to make a couple of different limits, right? And I'm going to write these in different colors so we can deal with them separately. We're going to do a limit as a approaches negative infinity of the integral from a to 0 of e to the x dx. And we'll add to that then a limit, and this time we'll do b approaches positive infinity of an integral from 0 to b of e to the x dx. And we should be pretty well guaranteed that this one that I'm doing here in blue is going to be infinite. This integral is going to diverge. This limit will be infinity, or it won't exist. But this one we might not be so sure about. So our integral of e to the x is what? It's just e to the x. And we'll do that from a to 0. And we'll add to that the limit is b approaches infinity of e to the x evaluated from 0 to b. And this part's going to be a limit as a approaches infinity of e to the 0 minus e to the, I'm sorry, that's negative infinity. Why did I write it? In fact, why did I write an infinity there? E to the a. Like I said, those are both negative infinities. And then here we have plus the limit as b approaches infinity of e to the b minus e to the 0. And so what happens with the one in red? E to the 0 is 1, right? And then this is minus e to the a, with a being negative infinity. So that becomes minus 1 over e to the infinity, which is
0.
And on the other side with the blue, we're going to get e to the infinity minus 1. And so this piece, the left-hand side, is just 1, plus this piece on the right-hand side is infinite. And so since this diverges, we can say that the entire integral diverges, which is what we would have guessed. But the left-hand side, if we go from negative infinity to 0, actually converges to a value of exactly 1 unit of area, which is pretty cool. Don't you think? The answer is yes to that question. Yes, you do think that's cool. All right. Let's do a couple of more of these. Let's see. I feel like, how about we do these two? Well, these two are pretty easy. Why don't you guys do these two on your own, and then we'll work together on the next couple. We get a little bit more difficult. What do you think? You think you could do these in 4 minutes, 5 minutes, something like that? Sounds good. I'll give you 5 minutes here to work on these. All right. Ready, go. So real quickly, if just in case somebody doesn't happen to be here today, you'll have to watch the period 5 lecture for that because I forgot to record the last 4 problems, and I will post that up in YouTube also. So let's continue now. So if we have an integrand that has an infinite discontinuity at one side of it, those are also improper integrals. So for example here, the integral from 0 to 1 of 1 over root x, there's an infinite discontinuity at x equals 0. And so we're going to do the same thing. We're going to turn this into a limit and just use a constant for that value. So we're going to rewrite this as a limit as a approaches 0, because that's where our asymptote is. And for this particular one, since our interval is from 0 to 1, we're going to be approaching 0 from the right-hand side. So we're going to integrate then from a to 1 of x to the negative 1/2 dx. Does that make sense to everybody? So we're going to replace the place where we have our infinite discontinuity with a limit or with a constant, and then make the limit as that constant approaches that x value. And we have to choose the correct side. So if my discontinuity was at 1, we'd have a limit as a approaches 1, and it'd be from the left because we'd be doing 0 to 1. Does that make sense to everyone? Okay. So x to the negative 1/2 should integrate to become what? Should be 2 root x, right? And we'll do that from a to 1, which will give us the limit as a approaches 0 from the right of 2 square roots of 1 minus 2 square roots of a, which is just what? As a approaches 0, square root of 0 is, as you come from the right-hand side, is what? That should be 0, so this just becomes a final result of 2. Everybody good there? Okay, and so this is what you will do if you have these infinite discontinuities as your limits. So if the discontinuity is at a, then that's the lower limit. You'll just have a limit as the some variable approaches a from the right of your integral, and if it's approaching b, where b is the upper limit, and that's where your vertical asymptote is, it'll be b is approaching, or c is approaching b from the left. And then we may need to split it in the middle if we have a vertical asymptote in the middle of our integral, and then we'll have to do both of these and use limits for both of them. Conceptually, okay? So let's do this one. Which of those 3 cases is this one fall under? Our vertical asymptote is at x equals 1, good. And so we need to split this up into 2 different ones, right? Our vertical asymptote, so this is x equals 1, and so we'll make this a limit as a approaches 1 from which direction to start with? From the left or from the right? Yeah, good. Nick, should be from the left. And this is just x minus 1 to the negative 2/3. I'm just gonna, we'll write x minus 1 to the negative 2/3. That's fine. Dx, and then we will add to that an integral. Oops, not an integral yet. A limit of b approaching 1 from the right now. The integral from 1 from b to 3, and same thing, x minus 1 to the negative 2/3 dx. Good. And what's the integral of x minus 1 to the negative 2/3? Should be just the cube root of x minus 1 divided by 1/3, right? So 3 cube roots of x minus 1. Everybody good with that or no? Okay, and so now we have a limit as a approaches 1 from the left of 3 cube roots a minus 1 minus 3 cube roots 0 minus 1 plus the limit as b approaches 1 from the right of 3 cube roots of 3 minus 1 minus 3 cube roots of b minus 1. And now we'll just evaluate it all out. As a goes towards 1, 3 cube roots of 0 is still 0, right? So this becomes 0 minus 3 cube roots of negative 1. So that's 0 minus negative 3. And then plus, here we have 3 cube roots of 2 minus, when we plug in 1, 0. So that gives us 3 plus 3 cube roots of 2. Everybody okay with that or no? No questions? All right, you want to do one of these on your own? This is the last one we're going to do for today, so I'll let you guys do this one on your own, then we'll work on it together. And if I forget to restart the recording, somebody yell at me right away. All right, ready to go. You got 2 minutes. So we have an asymptote at x equals 2. So we're going to have to do a limit as x, we'll call it a, approaches 2 from the left, because we're going from 1 to 2, of 1 to a of 1 over x minus 2 dx. Everybody good with that one? Or with that start? Giving us the limit as x approach, the limit as a approaches 2 from the left. Now it becomes natural log absolute value x minus 2 from 1 to a. And that gives us a limit as a approaches 2 from the left of natural log absolute value a minus 2 minus natural log absolute value of 1 minus 2. And as 2 goes to, or as a goes to 2 from the left-hand side, what do we end up with here? We end up approaching 0. So this is like what's happening to natural log as we approach 0 from the right. Because if I plug in a number very, very close to 2, this is getting very, very close to 0, but since it's absolute value, it's always from the positive side. And then minus the natural log of negative 1, which is just going to be 1 when I take its absolute value. And so this natural log as we approach 0 from the right is negative infinity, and then minus 0. And since this limit doesn't exist, we would then say that this diverges. Good or no?
Can you explain where you get the 0 from the right?
Mr. Batch, I don't think you're recording.
You don't think what?
I don't think you're recording, right?
No, I am. I restarted the recording. I can see the thing. It says I'm recording.
Okay, never mind.
Okay.
Like,
So to where I got this 0 from the right, so we're plugging in 2 from the left. So think about that as like, 1.9999999. Well, 1.9999999 minus 2 is negative 0.000000001. But since I'm taking the absolute value of that, it's like 0.000000001. And the closer I get to 2 from the left-hand side, the more 9s I add to that 1.999, the closer I get to 0, but I'm always coming from the right-hand side because that value is always positive. Does that make sense?
Yeah, thank you.
All right. Any other questions on that?